Hi, welcome again. This is video 10 of our video course series about statistics, and in the last video we have learned about linear regression with matrix equations, but for just one variable, for just x, and we have learned about the polynomial regression for the first order, which is we use a line equation for predictions, and also for second order polynomial, third order or higher order polynomials. But what if we have more than one variable? Let's say that we have three different variables and we call them x1, x2 and x3, and we have just one observable which we call it y, and let's create a data set with some number. For x1 we have 1, 2, 3, 4 and 5. For x2 we have 15, 22, 34, 65 and 103. For x3 we have 3, 8, 15, 28 and 51. And for y, for our dependent variable, x1, x2 and x3 are independent variables. We can change them to observe a variable which we call it y, and we have these numbers for our dependent variable y: 52, 94, 156 and 286 and 480. And let's say that we want to describe our observable by using all these three variables, x1, x2 and x3, and let's say that we have a prediction, we have a model which y hat equals b0, which is a constant which we call it intercept, b0 plus b1 x1 plus b2 x2 plus b3 x3, and we want to find the regression coefficients for all these three variables, and we want y1 will be equal to b0 plus b1 x1 1, which is the first line of x1, plus b2 x1 2, which is the first value for x2 variable, and b3 x1 3. And also we want y2 will be equal to b0 plus b1 x2 1, which is the second value of x1, and b2 x2 2 plus b3 x2 3. And it goes like this until yn will be equal to b0 plus b1 xn1, okay, plus b2 xn2 plus b3 xn3. So we have a set of equations. For a sample size lowercase n, we will have n times of equations, and we can easily express all these equations with a matrix equation to find the values of regression coefficients, right? So the main purpose is to find the values for b0, b1, b2 and b3, and also to test the quality of our prediction model, we want to find the value for R square. If we have an R square which is below than 0.5, then it means our model is bad. So we should use mean instead of our prediction model. But if we find a R square value which is above, which is greater than 0.5, then it means we can use our prediction model rather than the mean of y. So we can express all these equations with the matrix equation. So I'm going to define this area first. I'm not going to use this color. I will use this one. So first, for this part, I will define an X matrix, and for these terms, for B zeros, I'm going to use 1, and for these terms, I'm going to use x1, 1, and for the second term, I'm going to use x1, 2, and for the third and the last term, I'm going to use x1, 3. And for the second row, I'm going to use 1 again, and then x2, 1, x2, 2, and x2, 3, and it goes like this until 1, xn1, xn2, and xn3. It's the same procedure with the polynomial regression, but this time we use different variables, x1, x2, and x3. So this is a matrix, and this is X matrix. This is X matrix. And we are going to multiply this matrix with a vector which includes these regression coefficients, which are B0, B1, B2, and B3. Okay, which is equal to left hand side of these equations, which is y vector, and it includes y1, y2 until yn. Okay, this vector. Okay, and this is X matrix. This is B vector, and this is Y vector. So we have this equation, right? X matrix multiply with B vector equals Y vector. And now I just wanna multiply this equation from left side with transpose of X matrix. So it's X transpose here and X transpose here. So what is transpose of X matrix? We are gonna replace the rows with columns. We are gonna switch the direction to get the transpose matrix. So it's 1, 1, 1, x 1, 1, x 2, 1, x n 1, and x 1, 2, x 2, 2 up to x n 2, and x 1, 3, x 2, 3, and x n 3. This is X transpose. So all I want to do is to find X transpose times X and X transpose multiply with Y vector. if I find these two equations, these two operations, I can solve this problem to find the values for B0, B1, and B2 and B3, and then R square. So I'm going to do this to find these terms. I'm going to clear now this area. This will be the last video which I teach you the subjects, which I cover the subjects, and there will be no more subjects for this semester, for this course, but I'm gonna publish 1 or 2 more videos to explain your final homework. Okay, also I'm gonna clear this part. It takes too much time, I'm sorry, but I had to do this. I hope you understand this subject well, because it's required for your life as a computer scientist. So this is our main equation: x transpose times x times b vector equals x transpose times y vector. So for x transpose times x, we have this 1 1 1 x 1 1 x 2 1 x n1 x1 2 x2 2 x n2 x1 3 x2 3 x n3. And also for x matrix, we have 1 1 1 x 1 1 x 2 1 x n1 x 1 2 x 2 2 x n2 x1 3 x2 3 x n3. Questions and questions. Okay, and this will be equal to, so I'm going to use this color now. This will be equal to 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 1 up to this 1 times this one. So it will be equal to 1 plus 1 plus 1 plus 1 n times. So there will be a n here. And then this one times this x11 plus 1 times x21 plus 1 times x31 plus 1 times x41 up to 1 times xn1. So it will be equal to sum of x I1. Okay, and I will be equal to starting from 1 up to lowercase n. And for the third column, this will be 1 times x12 plus 1 times x22 plus 1 times x32 up to 1 times xn2. And this will be equal to sum of xi2. And for the third column, it's equal to 1 times x13 plus 1 times x23 up to 1 times xn3, and this will be equal to xi3. Okay. Okay. And for the second row, this time I'm gonna multiply this x11 with this 1 and plus x21 with this 1 up to xn1 times this one, and it makes sum of xi1, obviously. So with the same logic, I'm gonna multiply all these terms, and it makes, for example, for this cell, x11 times x11 plus x21 times x21 up to xn1 times xn1. So it will be equal to sum of xi1 square. Okay. And also we will have these kind of terms coming from x11 times x12 plus x21 times x22 plus xn1 times xn2, and it makes sum of xi1 times xi2. Okay, with the same logic, for this cell, xi1 times xi3. Okay, I think you get the idea now. Okay. For the third row, I'm going to start with x2s, and from this column we will have xi2, and for here xi1 times xi2. I want you to solve all this equation, and I want you to check the results by comparing with these results. So xi2 square, and for this cell xi2 times xi3. Okay, so for the last row we have sum of xi3 and xi1 times xi3 and xi2 times xi3, and for the last cell sum of xi3 square. This is our matrix. It's very easy to get, but I want you to be careful and check the results. Okay, for the second part, for the right hand side of this equation, we are gonna search for x transpose times y vector, and it will be the same matrix 1 1 1 x11 x21 up to xn1 x12 x22 up to xn2 x13 x23 xn3. With this time y vector, which includes y1, y2 and yn. Okay, now we will have 1 times y1 plus 1 times y2 up to 1 times y1. So we get the sum of yi. Okay, for the second row, x11 times y1 plus x21 times y2 up to xn1 times yn. So there will be a sum of xi1 yi. Okay, with the same way we get For the third row, sum of xi2 yi and sum of xi3 yi. Okay, we have the equation now. So all we have to do is calculate these sums and get the numbers and write them into the augmented matrix to solve them by using Gauss-Jordan elimination, right? So I'm going to calculate all these terms and write them in an augmented matrix. I'm going to clear now. You have the matrix. And don't panic, I have the numbers. I've already calculated them, so this part will be faster. Okay, now we have 5, 15, 239, 105, 15, 55, 936, 431, 239, 936. Okay, it will be a big number. And 3683, and for the right part we have 1068 4252 and 76182 35 and 736. Okay, this is our augmented matrix. And by using the Gauss-Jordan elimination, our aim is to get the unitary matrix for the left part, and for the numbers which we have at the right part, we will have them as our regression coefficients. So this is our matrix, and the first step is to get 0 instead of this 15. So this will be the first row, A1. This will be the second row, A2. And this is A3, the third row. This is A4, the fourth row. Okay. Our new second line, A2 prime, will be equal alt second row, alt values from second row, A2, these numbers, minus, we will need to multiply the first row with a constant, right? And this constant will be this number over this number. This is our rule. So this will be 15 over 5, A1. Okay. This is our step. This is our first step for Gauss-Jordan elimination. And it makes us to get 0 here and some other numbers for the rest of them. Okay, and I calculate them so I can write them. And when we apply this operation to our numbers in the second row, now we have 0 here, obviously. This is the purpose. 0, 10, 219, 116, and 1048. Okay, this is our new second row. Okay. And also for the third row, I'm gonna use this equation. A3 prime, the new values for third row will be equal to A3 minus the constant A1. Okay, I'm gonna use the first line to make this, and this number 0. This is our Gauss-Jordan elimination method. So this constant will be this number over this number. So it will be 239 over 5. Okay. So I will calculate this constant, and I'm going to multiply this first row, these numbers, with this constant, and then I'm going to add this first row to the current values for the third row to get the new values of third row. Okay, I calculated these numbers, and this will be 0, 219, 5275, and 2785, 25, 132. And I want you to check the results for every step. Okay, I want you to pause the video and apply the operations, apply the rule of Gauss-Jordan elimination, and then check your results by comparing them with mine. So I want you to check the results for every step. Okay, then I'm gonna find the new values for fourth row, the old values minus a constant times first row. So this constant now, this number or this number, so it will be 105 over 5. Okay, so the numbers are 0, 116, 2785, and 1478, 13308. Okay, but here is the question. I've used this number to make these three numbers 0. What if at the start, what if we have 0 here? What if we have 0 here instead of 5? Just remember the rules of Gauss-Jordan elimination. You can swap any rows. Okay, so if you have 0 in a pivot position of a matrix, you can swap the rows to each other. Okay, you can swap this row with the second row, and you can use this number now. But be careful, if you swap the positions of these rows, be careful. Also, we have a vector which includes the regression coefficients. If you swap these two rows, then this vector will become to this: B1, B0, B2, and B3. Be careful. Okay, be careful. When you change the position, you have also changed the position of these regression coefficients. It's a very important point. So now the purpose with this step, the purpose is to make 0 these two numbers. Okay, now I'm going to use this number, so the new values for third row a3 prime will be equal to a3 minus a constant times this time the second row a2. Okay, now if we go in this direction, okay, up to down, if we go in this direction, always we are going to use this number over this number. For the second part also we will go in this direction, then it will be the opposite, but if we go in this direction we are going to use this number over this number, so this constant will be again 219 over 10. Okay, so the new values for the third row will be, this 0 will be the same, so we have 0 here and also we have 0 here and it doesn't change, so we still have 0 here, but these numbers will change. Okay, and now we have 0, 479, 245 and 2180. Okay, so the new values for the fourth row, a4 prime will be equal to a4 minus a constant times a2, so this number over this number, so 116 over 10. Okay, and it makes, we still have 0 in the first column, and also we have 0 here, and it makes, okay, it makes 244.6 132.4 and 1151.2, and also I will correct these values. We have a 0.4 here and we have a 4.6 here and 8.7 here. Okay, now it comes to the third column, so we have this number now to make this number 0, so the new values for the fourth row a4 prime will be equal to a4 minus a constant times a3. Okay, and we go in this direction, so this number will be equal to this number over this number, so our constant is 244.6 over 478.7. Okay, so the new values for these three columns will be a 0 here, 7.4 and 37.1. Okay, now what is the purpose now? Our purpose is to make 0 this time this number, and this number by using this 7.4, and then we are gonna make this number 0 and this number 0 and this number 0, and we will have some numbers in just diagonal elements, and then we are gonna make it unitary matrix to get the values for regression coefficients. So the first purpose is make these three numbers 0. So this time we get the new values for the third row. A3 prime will be equal to A3 minus a constant A4. The values coming from the fourth row. So, but this time we go in this direction. So we get our constant by using just a line between these two numbers. So this constant will be 244.6 over 7.4. Okay, this will be the opposite if we go to this direction. Okay, this direction will be equal to this number over this number, the opposite. But if we go to this direction from down to up, then we can use this constant directly. Okay, so I'm gonna clear. The new values for sorry. This number doesn't change because we have 0 here, but these two numbers will change. So we have 0 and 957.4. Okay, now the aim is make this 116 0. So our operation will be the new values of the second row. A2 prime will be equal to A2 minus a constant times A4. Okay, and this constant will be 116 over 7.4. Okay, I think you get the idea. So now we can change the values for this row. There will be a 0 here and 4, 6, 8. Okay, then we can go faster now. We are going to change the values of first row by using the fourth row. So this number will change, this number will change, and they will be 0 and 5, 4, 3, and I hope you check the values with me. So in the next step, I'm gonna make this number 0 and then this number 0 by using this number. So this number will be 0 and this 0 won't change, so this number will be 30. And then we are going to change these two numbers and then this 15 by using this 10, and we will have 0 and 0 here, and for the right hand side we have 20. Okay, now we have the numbers in diagonal elements, and then we have just zeros in our matrix. And now we are going to make this 5, but this time not 0, this 5 1. Okay, so the new values for the first row will be equal to old values times 1 over 5, and then the new values for the second row will be equal to A2 times 1 over 10, and for the third row A3 times 1 over 478.7, and for A4 times 1 over 7.4. And these operations make these numbers 1. So we get the unitary matrix at the left hand side of our augmented matrix. So we have 1, 1, 1, and 1. Obviously these numbers will change by using these operations, and they will be very simple numbers: 4, 3, 2, and 5. Okay, now we have solved our problem, and we have our regression coefficients now So our model will be y hat equals b0, so it's 4, plus 3 times x1 plus 2 times x2 plus 5 times x3. Okay, here is the question: what is the strongest variable for our model? What is the strongest variable? I want you to pause the video now and think about it. What is the strongest variable? If we have, and also we can express this model with this notation: x1, x2 and x3. If we have all zeros for all three variables, we get just 4. Okay, if we get 0 0, okay, let's start with 1 0 0, then it makes 7. If we have 0 1 0, then it makes 6. For 0 0 1, it makes 9. Okay, which is the strongest now? Obviously the strongest variable is x3. Okay, so we can understand this from our regression coefficients, and also we can calculate the r-square value. R-square value will be equal to SSR over SST, which equals the sum of differences between y I hat minus y bar, which is the mean of y points, square over sum of the difference between yi over y bar square. Okay, I have produced this data by using this constants, so there will be an r square equals 1 for this question, but most of the time you will get an r square between, I think, 0.7 and 0.95. Okay, this was a question, this was an exercise. Also, we can have some how can I say, some model, like let's say that we have a data set for x1 and x2. This time we'll have just two variables, and 1 2 3 4 and 5, 4 4 9 9 9 and 13 22 37 63 and 90. So it doesn't have to include a b0. So we can define a model like this: b1 x1 square plus b2 square root of x2. So it doesn't has to be a regular equation. Okay, it doesn't has to be a regular equation. So we can define any equation that we want. So for this model, we have our x matrix like this, right? For these terms, we will have x11 square, x21 square, x31 square up to xn1 square, and from this term we will have x1 to square root and square root of x2 to square root of x32 up to square root of x and 2. This will be our x matrix. So our x transpose will be equal to, if we have this matrix, x transpose will be equal to x11 square up to x n1 square, and starting with x 1 to square root x n2 square root. This will be our x transpose, and if we multiply this x transpose with our x matrix, we will get, when you make these operations, we will get sum of x I1 to the 4 and sum of x I1 square multiply with square root of x I2 and sum of x I1 square square root of x I2 and also the sum of x I2s. Okay, this is our x transpose times x, and also we will need x transpose times y vector, which will be equal to sum of x I1 square y1 and square root of x I2 yi. Okay, so when we calculate these numbers to get our augmented matrix, we will have, I'm gonna use this color now, we will have 979, 151 and 151 and 30, and for the right side 3, 6, 92 and 603. Sorry, this will be our augmented matrix. So this is an easy operation. So the first purpose to make this number 0 and then to make this number 0 and then make this number 1 and then this number 1. This is a 2 by 2 matrix. So the new values for the second row a2 prime will be equal to a2 minus a constant times a1, and this constant, if we go in this direction, this constant will be 151 over 979. Okay, and for the second part, now after this operation we will get 979, 151, 0 and 6.71, 3692 and 33.55. Now this is our augmented matrix, and for the next step we will a1 prime will be equal to a1 minus a constant times a2, but this time we go in this direction from down to up, so our constant will be this number, so 151 over 6.71. Okay, after this step we get our augmented matrix as like this. Okay, now we make these two numbers 1. So our operations will be the new values for the first row will be equal to old values times 1 over 979, and the new values for the second row will be equal to old values times 1 over 6.71, and then we get our final augmented matrix 1 0 0 1 3 5. So our model is y hat equals 3 x x1 square plus 5 square root of x2. Okay. So it doesn't has to be a polynomial, or it doesn't has to be a regular expression. So you can define any model that you want. And also you can have a model like this. For example, you can have a model like y hat equals some constant c times exponential of some constant a times x. Okay, now what can we do? Okay, we can take natural algorithm of the both side, so we can ln of the left hand side and right hand side, so it makes ln y equals ln c plus ax. So we can call this ln y as y prime equals, we can call this ln c because c is a constant, so ln c will be a constant too. We can call this constant by using b0, plus we can call this constant as b1. It doesn't make any difference, so b1x. So we get our line equation. Okay, and this process is called data linearization. Data linearization. Okay, and also we can have an equation like this: y equals c times x to the power of a, but this time we just take the logarithm of both sides. So logarithm of c times x to a, and it makes log y log c plus a times log x. Okay, then we can call this y prime plus b0 for this part plus b1 for this part, but we still have logarithm of x. So we can transform our data from this to this, log x and log y. Okay, to do our linear regression, and it's called data linearization. And that's all. We have covered all the subjects that we have aimed at the start of our course. So there will be a video for your final homework, but the subjects are that. Okay, we have done. So see you later. See you in the next video. Take care of yourself and stay at your homes. See you.